Okay guys, in this video we're going to be talking about Dalton's law of partial pressures, which applies to mixtures of ideal gases. And so Dalton's law tells us that the total pressure of an ideal gas mixture is just the sum of so-called partial pressures of the different gas components. So the idea here is that we've got a mixture of gases made up of several ideal gases. And the total pressure is a sum, that's what this funny symbol is here, a sum of partial pressures, where the number or the subscript I represents an index for the different gas components. So if you had two gas components, you would take the partial pressure of the first component plus the partial pressure of the second component. If you had three components, you'd add up three partial pressures. Or if you had a mixture of 5 different gases, you would add up 5 partial pressures. Each partial pressure satisfies its own version of the ideal gas law. And so Pi is just the number of moles of that component I times R times T divided by volume. That's just the ideal gas law. Because ideal gases don't interact with one another, we can substitute in this expression for Pi and then factor out the R and the T in the volume and then add up the number of moles of gas to give us this equation where the mixture of the pressure of the gaseous mixture is just the total number of moles of gas that you have times R times T divided by the volume. So there's two different levels in which you can use the ideal gas law. You can use it to calculate the partial pressure of an individual ideal gas component of the mixture, or you can use it at the level of the total mixture where you consider the total number of moles of gas. Either way is fine. Either way works. A quantity that we use to express the concentration of a gas in the gaseous mixture is called the mole fraction. It's a unitless quantity. The mole fraction of the ith gas component is the number of moles of that component divided by the total number of moles of gas. That's why it's called the mole fraction, right? It's the part, the number of moles of component I, divided by the total number of moles of gas that you have. Well, using these equations, you can show that the mole fraction is also equal to the partial pressure of the gas divided by the total pressure of the gas mixture. And you can rearrange this equation to say that the partial pressure of the gas, I, is equal to the mole fraction of that component times the total pressure of the gas mixture. Okay, so there's a number of equations that we can use here when we're talking about gaseous mixtures, and we're going to go through some of those in these problems. So here we've got a liter of dry air, which means that there's no water vapor in the air. It's at 25 degrees Celsius, and the total pressure is 786 millimeters of mercury. This gas mixture contains 0.925 grams of nitrogen, plus other gases, which include oxygen, argon, and carbon dioxide. We're being asked to calculate the partial pressure in millimeters of mercury for the nitrogen gas. And so what we can do is use the ideal gas law at the level of the partial pressures. So the partial pressure of the nitrogen gas is going to be equal to the number of moles of nitrogen gas times R times T divided by the volume of the mixture. Okay? Now they've given us the mass, and so we can write that as, or they've given us the mass, so we can write the number of moles of gas as 0.925 grams divided by the molar mass of diatomic nitrogen, which is 28 grams per mole. Okay, so that's going to be the number of moles of nitrogen we have. We'll take that times the gas constant, 0.0821 liters ATMs per mole Kelvin. We'll take that times the temperature, which is going to be 298 Kelvin. Need to convert that 25 degrees Celsius to Kelvin units. And then we're going to divide by the volume, which is just 1 liter. And so this is going to give us the partial pressure in units of, this will be in units of atmospheres. And so I'm getting 0.808 ATMs. And to get that in units of millimeters of mercury, we would say 760 millimeters of mercury for every 1 ATM. And so I'm getting 614 millimeters of mercury out of my calculation. Next, they want us to calculate the mole fraction of the nitrogen. Okay, and so the mole fraction of the nitrogen is going to be equal to the partial pressure of the nitrogen divided by the total pressure. Okay, so we've got 614 for the partial pressure, and the total pressure was 786. And so I'm getting a fraction of 0.781. And in terms of a percentage, that would be 78.1%. So this mixture is 78.1% nitrogen. Let's see. Next up, we've got another gas mixture. This one consists of oxygen gas and CO2. So we have a certain volume, 10-liter flask. It contains 1.031 grams of oxygen and 0.572 grams of CO2 at 18 degrees Celsius. What are the partial pressures of the oxygen and the carbon dioxide? What is the total pressure? What is the mole fraction of oxygen in the mixture? So they want us to calculate quite a bit. Let's see. Well, to get these quantities, we need to know the number of moles of each component. And so let's calculate that first. Let's just separately calculate the number of moles of O2, which is going to be the mass of O2 divided by the molar mass of O2. So that's 1.031 grams divided by 32 grams per mole. Get that number, and we'll do the same thing for the CO2, mass of the CO2 divided by the molar mass of CO2. Here we've got 0.572 grams divided by, let's add that up very quickly, 44. Let's see, it'd be 44.01 grams per mole. 0.0130 moles. And the first one, 1.031 divided by 32. Just going to check this number. Yeah. So we have the number of moles of each component. They want us to, let's calculate the total number of moles. That's helpful. So we'll just add those together. So I'm just going to add these two numbers up, 0.0322 plus 0.0130. So that's the total. Let's calculate the total pressure. P total is number of moles total times R times T divided by the volume. Okay, so we'll have the 0.0452 moles times the gas constant times the temperature, 18. We need to convert that to Kelvin. I'm getting 291 Kelvin. And then we'll divide by the 10 liters. If I've done that correctly, I'm getting 0.108 ATMs out of the calculation. Just check one more time. Yes. So that's the total pressure. What would be the partial pressures of O2 and CO2? Well, since we have the moles already, and we also need to calculate the mole fractions, let's just calculate the mole fractions of each component. So we'll take the mole fraction of O2 will be the number of moles of O2 divided by N total. So I'm going to take the 0.0322 and divide it by the 0.0452. That's giving me 0.712 for the fraction, and then we'll do the same thing for the CO2. Number of moles of CO2 divided by N total. So now I'll take this number, 0.013, and divide it by the total, and I'm getting 0.288 for that fraction. To get the partial pressures of O2 and CO2, I'm going to take the mole fraction times the total pressure. I can do the same thing for the CO2. So I'm going to take the total pressure, 0.108, multiply it by 0.712, (0.0769 ATMs), and then for the CO2, I'll take the 0.288 times the total pressure, 0.108, 0.0311 ATMs. Okay, so I think that was everything that we needed to calculate. We didn't do it in the order that they asked, but this illustrates using mole fractions. It illustrates calculating the total pressure of a gaseous mixture and calculating partial pressures from molar fractions, or from mole fractions. Let's see, let's talk about this conceptual question here. Okay, so we have a rigid flask that's equipped with a valve, and it contains 3 moles of hydrogen gas. And what we're going to do next is introduce 3 moles of argon gas, and then seal the flask up again. What happens to the pressure of just the H2 gas as we introduce the argon? If it changes, by what factor does it change? Well, this is an ideal gas mixture. Okay, and so the hydrogen gas and the argon gas don't interact with one another at all. They're independent of each other. And so the pressure of the hydrogen gas isn't going to change just because you introduce argon gas. It's going to have the same partial pressure that it did before. How do the pressures of the argon and the hydrogen compare? Well, since we assume that the temperature is the same and the volume of the container doesn't change, when we introduce 3 moles of hydrogen, when we introduce 3 moles of argon gas to the 3 moles of hydrogen gas, since they have the same number of moles, they have the same volume, they have the same temperature, we would expect the pressure, the partial pressure of the argon to be equal to that of the hydrogen gas. So they would have the same value of the partial pressure. How does the total pressure of the flask relate to the partial pressures of the two gases? Well, total pressure is going to be the sum of the partial pressure of the argon plus the partial pressure of the hydrogen. Okay, if these two pressures are the same value, then the total pressure is going to be twice the value of the argon, or you could say twice the value of the hydrogen, since those two pressures are the same. I'm going to go ahead and stop this video here, and we'll talk about collecting gases over water, as well as gaseous stoichiometry problems in the next video.